Professor Subrahmanyam.
Sure. This is going to be a second talk, this seminar, this academic year about geometric complexity theory, which aims at certain complexity problems using algebraic geometry and representation theory. And I talked. The first one was in October when I talked about this and explained connections between various complexity measures for forms and orbits and orbit closures. And today, my colleague from Chennai Mathematical Institute will focus mostly specifically on the problem of describing this orbit closures of polynomials and okay, so let's start.
Yeah. Okay. Thanks, Fedor. Thanks for the invitation. Yeah. So what I will do is I have prepared some slides, but I will also scribble when needed and write when needed. Yeah, so please interrupt me whenever you have questions. The plan is that I would like to tell you about some recent work. This is joint with Bharat and Milind. Bharat and Milind are both at the Indian Institute of Technology in Mumbai. So I presume they're online. And if there are questions on the chat, please somebody interrupt me and tell me there is a question and please read out the question, then we will try and answer. Yeah, thanks. Yeah, so this is I hope my screen is visible. Yeah. Is the screen visible?
Yes.
Yes. Very good, very clear. Yeah.
Yeah. Okay. So so I have sort of broken up the outline in the following way. So since Fedor says he's already sort of introduced geometric complexity theory, perhaps I can rush to the first 9 slides, which is really the motivation, which defines the problem and the motivation for us from computer science. And then I will do a brief review of GCT and other approaches towards solving algebraic complexity theory problems. Again, with apologies, I will not be able to cover all possible ways that people have sort of tried to tackle this. It's, of course, biased by my own interests and what I know. There is a lot I don't know. Please excuse me for that. Yeah, and then what I will do is I will present what Bharat, Milind and me have called Lie algebraic methods, which we set out to do somewhere in 22. And then I will describe the following, which is all new: alignment, then the notion of intermediate varieties, and I will explain why that is important. Yeah. Okay, so here we go. So the setting is the following. So for us, G will be a connected reductive group over C. So for most of the talk, you can think of G as GLN for some n or GLM for some n, the general linear group. So that's really all we use. Yeah. What we are given is a representation of G on a vector space. And that representation I denote here by rho. So now once I have this representation, so a representation for us is just a homomorphism from the group G to GLV, the general linear group on V, invertible matrices of dimension of size, dimension V cross dimension V. Yeah, and okay, so now the point, so given a point Y in V, we can talk of its orbit. The orbit of Y is the following. The orbit of Y is all points that I can reach via G. So this is the orbit of Y. And of course, we know that the orbit need not be closed. It is what is called a constructible set in geometry. So of interest for us is the orbit closure of Y. Actually, the orbit closure taken either in Zariski topology or in Euclidean topology. A good example for this is the GLN action on the standard representation Cn, for example. Then, of course, if I give you any non-zero vector, its orbit is all of Cn. I can reach any non-zero vector. So the orbit closure also picks up the point, the zero vector inside this vector space. Yet another example which most of you are probably familiar with and know it, is the action of GLN on n cross n matrices, which I denote by Mn. And Jn, if I denote as the Jordan block with ones on the super diagonal, then this is also known that under conjugation, you'll pick up the set of all nilpotent matrices. Yeah. So this is the question of interest for us. We want, let me go back. Yeah. Yeah. So the question of interest is the following. I give you 2 points in this vector space V, and I ask you, is X in the orbit closure of Y? Again, orbit closure with respect to the G action that we have defined. Yes. The problem, so we would want somewhat computationally also to be able to solve this, and we expect that the answers, that this problem is generally wide, but what we will observe is that the stabilizer of X, which I call G of X, and the stabilizer of Y, which I call G of Y, these stabilizers are distinctive in a way I will describe very soon. So what then we expect a good answer for this. Yeah. So sometimes we may want to do this in the vector space. Sometimes we want to do it in the projectivized vector space over V. Yeah, and I mean, it is only in this slide that I'm being a bit careful. I write square brackets X for the corresponding point in projective space, and square bracket Y for the corresponding point, point corresponding to Y in projective space. And then the question is, does this projective point belong to the orbit closure of Y? Yeah, so the motivation for us is from algebraic complexity theory. So I hope there are no questions. So is the problem of interest clear? Could I go ahead, or are there questions right here? So, no, then I'll just go ahead. Okay. So the motivation, as I said, comes to us from algebraic circuits, algebraic complexity circuit theory. So what is an algebraic circuit? An algebraic circuit is a graph of this kind, which is really a graph that sort of. Sorry, I knew I'm going to do this. Yeah. Yeah, okay. So it's a graph where, think of this as a graph where the edges are going up, actually. So there are variables and constants on nodes, and every node is labeled with a variable or a constant, or with pluses and multiplication. And there are constants on edges also. These constants for us come from the underlying field. And they compute a natural function in the obvious way. For example, this node computes. So if I look at this node, it computes x3 plus 1, and then this node computes x2s, and this node now computes x3 plus 1 times x2, and so on, and out pops out here a function on the variables. So this is what we call an algebraic circuit. And then if I look at an algebraic circuit, for an algebraic circuit, there are 2 parameters that are of interest, namely the number of nodes that I have in this graph. So think of this as an acyclic graph. That is important, and it will be acyclic because my edges are all going upwards. Of interest is the number of edges in this node, or the number of nodes plus edges, if you want. Yeah, and that is of interest. That is what I call the size of this graph. And there is this interesting complexity class called VP, which is the set of all sequences of polynomials. So you have a sequence of polynomials Fn for an infinite number of n, and the class VP is defined as the sequence of polynomials for which there is a way to compute the nth element in that sequence using a circuit which has size at most n to the c for some constant c. So the constant c should be independent of n, of course. Yeah, so for example, if I look at this polynomial x1 to xn, x1 times x2 times xn, one can easily show that this is computable by a small circuit, by a linear size circuit. This polynomial also turns out we can actually compute it quite efficiently and quite easily. Yeah, the second one. The third one, the way it has been written, it is not clear that we can actually compute it easily. But as you will observe, so what we are doing is taking all possible products of in variables and summing them up. So it turns out there is a very simple sort of circuit which computes it, which actually computes it in the following way. You compute in this, you compute first 1 plus x1 for 1 plus xi for every I, and take the product. And of course, then if you look at this, this is a small size circuit that computes this function, this polynomial function fn. And this, like I said, it is important for us that we are looking at a family of polynomials. Yeah, and the family in some sense is sort of similar kinds of polynomials for every n. Yeah, so this is our motivation.
Yeah, the question, what is size? I also want to ask.
What is size? Yeah, sure. Size is the number of nodes. So each of these dots here is a node in my this thing, and the number of edges in this graph. So the size is, so for example, in this circuit that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 nodes. And then you can count the number of edges that are present. 3 from here, 3 here, another 3 here, 2 here, and so on. So is it now clear? The number of nodes and the number of edges, the number of vertices and the number of edges in this circuit. Is that clear? Or should I explain it more? The size is just the number of vertices and the number of edges in this graph. So maybe I should just write it down. Size of this circuit is number of nodes plus number of edges. Is that clear? Sorry?
So I mean that because number of edge is less than equal number of node square,
yes.
right?
You can replace it by just twice them. So we are assuming that from every node that I have here, we just have some number of edges, and we just count the number of edges. That's also enough. Yeah. So you don't have to count all the nodes. Yeah. But if you want to be precise, then this is the way you will calculate.
Sure.
So important. Yeah. 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 And everything is anyway in the order notation. So we don't have to worry too much, because we are only interested in this actually. We are interested in showing that there is actually a way of actually computing it. If I give you n variables, you want to compute it in a circuit which has size n to the c for some constant c. So O of n to the c if you want. Yeah, is that clear?
Yes.
Yeah, I'll just go ahead. Yeah, okay, sure. Thanks. Yeah, so now an important polynomial which is of interest, of course, to everyone is the determinant polynomial. Now, this is a polynomial on n squared variables of degree n. Yeah, and so it turns out that the determinant is universal in the sense that any polynomial can be computed as the determinant of a square matrix, provided I allow what are called affine linear functions. If I allow affine linear functions, then every polynomial can be computed as the determinant. So you're saying, give me a polynomial, I will write down a square matrix whose entries are affine linear function in the variables of the polynomial. And when I take the determinant of that, I get the polynomial that you want, that you started with. So every polynomial can be computed. That is not difficult to see, but I'm not going to do that. But of interest is the following then. If I give you a polynomial f, and I ask you, well, what is the size of the smallest? I want to write down a matrix whose entries are affine linear functions in the variables of the polynomial. what is the size of the matrix that I can write? What is the smallest size that I can actually write? Yeah, so that is called the determinantal complexity of the function f. So given a function f, you want to write down a matrix whose entries are all affine linear functions in the variables of the polynomial, so that when I take the determinant of the matrix I have written, I get back my original polynomial f. Yeah, and the size of the smallest matrix you can write is what is called the determinantal complexity of the function f, of the polynomial f. So for example, if I look at this polynomial, x1 times x2 times xn, of course I can write down a diagonal matrix where the variables appear here. And to compute this polynomial, for every n, I require size determinantal complexity is n. So then n by n matrix will do it. So determinantal complexity is important. And that gives us another complexity class, which is called VBP in complexity theory. And that is not so important actually. But what is of, so look at all polynomial. So now look at a polynomial family. Polynomial family is, you're given a family of functions and you want every polynomial in that family, you want to write down a matrix whose size is polynomial in the number of variables that that function has. Yeah, and you want to know whether this is true for this function, this polynomial family that is given to you. Is it true that as a function of n, you can write down matrices whose sizes grow as into some constant for every n? Yeah, and it is not clear that you can do this for every polynomial family. Yeah, but this is of importance to computer scientists. Yeah. So one may ask, are there polynomials which you expect are not easy to write down as determinants? It turns out yes, that if I pick up a random polynomial, then it was shown in fact, he is in your institute, Pavel is in your institute. So he, along with Yehuda, showed that a random polynomial is actually hard. For a random polynomial, you will require an if I give you a polynomial in n variables, a random polynomial with 0, 1 coefficients will require exponential size. Determinant to compute.
Could you explain me what do you mean by a random polynomial?
A random polynomial, so coefficients. So I mean, so if you don't mind, I'll just go ahead. Don't worry about this at this point. We will go ahead. Yeah. So, but of interest is an explicit. What we want in complexity theory is an explicit polynomial. We want an explicit polynomial which is hard. Can you show me a particular polynomial family which is hard? That is really the question of interest. And the candidate that we have is really the permanent of an m by n matrix. So for every m, I can define the permanent of a matrix, correct? I can define the permanent. The permanent is really written like the determinant, excepting that I don't have the sign in front, the sign of pi in front of it. I take the constant 1 as the sign. So you run over all permutations of the symmetric group on m letters, and now pick up. So you write down an m by n matrix, take all permutations of m and pick out these corresponding variables from the rows, multiply them out and add them over all permutations. So that gives you this permanent. And of course, I can define this for every integer m, every non-negative, every positive integer m. So this gives me a family of polynomials, which I will call per m, one for every m. And we believe that these polynomials cannot have small size determinants which compute them. So is the goal clear? So we would like to actually answer this question. Is the permanent, can you show that the permanent cannot be computed by small size determinant? And that is really Valiant's conjecture, that the determinantal complexity of the permanent function is exponential in n. That is really what algebraic complexity theory would like to actually show that is really one of the holy grails, if you want, of algebraic complexity theory. So is this question clear? Yeah, are there questions on this? So you have this permanent family.
I only asked the Hurubes and the Yahudov reason does not related to this conjecture. Random polynomials, that means that's from my point of view, that's of course it is a precise definition. I would say that's almost.
Yeah, so that is not so important. No, what we need, no, it's a very important result. I'm not denying the importance of the result. All I'm saying, so there are lots of polynomials which are hard to compute as small size. There are lots of polynomials you can write down, which you believe are going to be hard to write down as small size determinants.
They didn't do anything with determinant complexity. Half here that only computed by size.
Sorry? No, we are talking about the determinantal complexity.
Yeah, and the Hurubet, Yahudov didn't do anything. It's a determinant complexity.
Yes. So their result also shows it for the determinantal complexity, but it is only for, but there is no explicit family like we have written down here.
Yeah.
We want a family of polynomials, one for every m, and we want some nice expression for every polynomial in the family, an expression like we have for the permanent. So that's what I mean by family. So there are reasons one goes for this, but let us just stick to this and ask, can you show that this family of polynomials cannot have small size determinants?
Also, a remark, I don't think the result holds for every field.
Okay. It only works over integers and complex numbers, is it? I don't know.
Yes, that's a good question. So, yeah, well, I think it probably holds for finite fields, something like this, no? But I'm not sure.
I mean, maybe somebody else in the audience would know. One of my colleagues would know. I don't remember. Yeah.
Please repeat the question. I missed the question. What was the question?
What was their exact statement? Was it over finite fields? Was it over complex numbers?
Of this Rubesh-Yahudov result?
Yes.
Not over finite field.
I don't remember it. Yeah, I don't really remember.
I think it is over finite field.
Okay. Yeah. But we will, our interest is really to actually show that this is really a belief. It is believed that this polynomial cannot have small size determinants, this polynomial family. And this is what algebraic complexity theorists are trying to prove for a very, very long time. And as you can say, since almost, 45 years now? Yeah, since about almost 45 years, people have been trying this. Yeah, so this is, so there have been various approaches. One of the approaches, what is called geometric complexity theory, which I will describe. And here, one looks at the following this was the approach that was laid down by Mulmuli and Sohoni. So this was also something that Strassen had in mind long time ago. But they seem to have, so what Mulmuli and Sohoni do is to lay down the problem very carefully, and then they did a lot of other work on top of that. So what is their idea? Their idea is now to look at these as orbit closure problems. So let me just describe that very briefly. So now you fix this vector space of n squared dimensions over C. You look at polynomials of degree n in the variables, in these n squared variables. Let us assume that the variables are numbered so that they are x11, x12, all the way down to xnn. Yeah. Now, of course, so I'm looking at this group GLW, which is n squared by n squared matrices. Yeah, n squared by n squared matrices. N squared by n squared matrices. Now, of course, there is a natural action of GL of that group G on this standard representation. It also, therefore, acts on the dual space and on polynomials of degree n on the dual space. Yeah. So one particular polynomial in this vector space V is the determinant polynomial. It's a polynomial of degree n in the n squared variables that are present. Now, you have this natural representation of G on this vector space, which sends a polynomial which does the following. You take an invertible matrix and send every polynomial f to the polynomial f composed with n. Yeah. So now note that this is an n squared by n squared matrix, and f composed with that gives me a new polynomial, and this polynomial under this matrix goes to this. So therefore it goes to another element here, and as if I were to write down the explicit representation, it's going to be a huge polynomial of degree of size n squared plus n minus 1, choose n minus 1 or something like that. Yeah. So I can do this for monomials, and therefore I can extend it. Yeah. Now, inside this vector space, as I said, I can look at any particular polynomial f and I can ask for its orbit closure. So viewed this way, I can ask for the orbit closure of the determinant polynomial inside. So determinant is a polynomial here in this vector space V. I can say, well, look at the orbit of the determinant polynomial under this GLW and look at its orbit closure. Yeah. Now, the permanent polynomial is a polynomial of degree m in m squared variables. Let us do the following. Let me embed the m squared variables of the permanent as the first m cross m variables of the determinant. But of course, now this is only a degree m polynomial. Now take the last, maybe this variable that I have, and multiply the permanent with this monomial. Now it becomes a polynomial of degree n in these n squared variables. And I can ask, does this polynomial, which is now a polynomial sitting in this vector space V, does this belong to the orbit closure of the determinant? This is the way Bulbule and Soni set up the problem. They conjecture that this polynomial xnn times n minus m times the permanent is not in the orbit closure of the determinant unless n is exponential in n. That is the way they set up this problem. So if you have any questions on this, please interrupt me. Yeah. And the important contribution, one of their main contributions is to observe that these polynomials that we have looked at, which is determinant and permanent, they have distinctive stabilizers. By distinctive stabilizers, I mean they are the only forms. So the determinant polynomial is, for example, the only form up to multiplication by a constant whose stabilizer in this GLW is what the stabilizer of the determinant is. The determinant, one can write down explicitly what its stabilizer is, and one can show that the only polynomial with that stabilizer is the determinant polynomial. Likewise, if I look at the permanent of an m by m matrix, it is the only polynomial. Now, when I'm looking at the permanent of an n by m matrix, of course, I have to look at the action of m squared by m squared invertible matrices. And one can then, they write down the stabilizer of the permanent, which was known, and they actually show that it is the only polynomial that stabilized. Yeah? So the belief is that a statement of this kind, you should be able to show just using the group theory of the stabilizers of the permanent and the stabilizers of the determinant. That was their main, that is their main sort of, if you want, this is, so their statement is that the distinctive stabilizer should allow you to conclude this. And that is the USP of GCT. So, so is the question, is the approach that GCT lays down clear? Please interrupt me if you have questions.
What was the definition of distinctive stabilizer?
What is the definition? It means that it is, so let me do it for the determinant. For the determinant, I can write down what the stabilizer is precisely. So you grant me that. Then if I look for any other polynomial in this vector space V, and I ask, what are there other polynomials which have the same stabilizer? Yeah. The only other polynomials which have the same stabilizer as the determinant is the determinant multiplied by a constant.
Okay.
Yeah, okay. Any other questions? Okay, then should I go ahead? Okay. Okay, so here is the picture. So what is known is the following, that if I look at polynomials and I look at a polynomial f and I look at its orbit closure, then it is known that if some polynomial comes into the orbit closure of another polynomial, like in this case, if g comes into the orbit closure of f, then in fact there is a one parameter family, yeah, an element of n w cross tensor product with ct, such that when I apply this one parameter family to f, g will be the smallest degree term. They will be the coefficient of the smallest degree term in t. G will appear as the coefficient. This will be t raised to a times g plus t raised to b times fb plus other things. Yeah. So if I look at a one parameter family, then if g appears in the orbit closure, there is a one parameter family that I can apply to f so that g turns out to be the smallest degree coefficient in t. Yeah. Now, what Milind and Ketan Mulmule's approach was somehow to try and connect up the stabilizers of f and stabilizers of g. Yeah. So what Valiant's result tells you is that if this polynomial xnn to the n minus m times the permanent is in fact computable as a small size determinant is computable as the determinant of a matrix with affine linear forms, then in fact what one can show is that that is equivalent to this, that there is a one parameter family, yeah, then if the determinant is in the orbit close, has a small size determinantal complexity, then in fact I can homogenize the determinant so that I will get because there are constants, you see, that's what Valiant tells you. Then in fact Valiant's result can be interpreted this way, which is saying that if the permanent has a determinant representation as an n cross n determinant, then this polynomial will appear in the orbit closure of the determinant under a one parameter family, under a one parameter subgroup. Sorry. So let me repeat it. If the permanent has an expression, permanent of an m by m matrix has an expression as a determinant of an n by n matrix with affine linear forms in the variables x11 to xnn, then I can replace the constants that appear there by this variable, assuming that the permanent variables are here and this variable does not appear in the permanent. If there is a small size, if there is an n cross n determinant which captures the permanent, then in fact one can show that there is a one parameter subgroup that drives the determinant into this polynomial, yeah, up to orbit. I mean, you might have to conjugate the determinant, but that is not an issue. Yeah. So if the determinant has an n, if the permanent has an n cross n determinant, then in fact this polynomial is in the orbit closure of the determinant under a one parameter subgroup. That is the correspondence to that is an equivalent statement of what Wheeland has shown. Yeah. So what one wants, therefore, is to actually show that there is no one parameter. So if I want to show that G is not in the orbit closure of F, if I want to show that the permanent does not have a small size determinant, then I have to show that there is no one parameter subgroup which drives. So my F is going to be my determinant here. My G is going to be my padded permanent, padded because I have jacked up the degree by this. Then there is no one parameter subgroup which drives the determinant into the permanent, which picks up the padded permanent as its lowest degree coefficient in T. That is the GCT approach. So is this clear?
Yeah, maybe. Well, it's worth mentioning that if you do not take closure of the orbit
Yes.
of determinant, then you
Yes.
can immediately show that
Yes.
permanent is not there.
Correct.
By
If
looking
I
at
don't-
stabilizers.
Yes, by just looking at stabilizers. Correct. Correct. Yeah, that's a point. Yes. So there are other approaches to actually solving Wheeland's conjecture. So I will just list down a few here. One is the algebraic complexity theory approach, which is very combinatorial but has met with a lot of success. Starting off by, I have not, again, it's, as I said, I have not listed all names. Some of the names that came to my mind as I was making the slides: Ranras, Victor Sen, Amesh Pilka, Manindra Agarwal, Saxena, recently Pranjal Datta, Nutan Limaye, Pascal Coiron, Srinivasan, a lot of people actually. Then there is this approach by Rasaire, McKinnon, Landsberg, who sort of take a geometric approach to solving this problem. Then in GCT itself, they want to pose this as, again, I'm not going to go into great details in GCT at this point. They want to show that no such surjection exists, because if G is in the orbit closure of the determinant, then in fact, there would be a surjective map from the coordinate ring of the orbit closure of F to the coordinate ring of the orbit closure of G. And since both these orbit closures are G stable orbit closures for the G we are looking at, one could look at G representations which occur in this orbit closure, in the orbit closure of the permanent, jacked up permanent, which do not occur. Suppose I find some G module which occurs here, but that G module does not appear here, it will tell me there is no such surjection that is possible. Yeah. So that was the approach that Ketan and Milne laid out. This was the approach that they said, and they formulated a bunch of conjectures saying that in fact you should be able to find some G module which occurs in this, which does not occur in this, whenever n is sub-exponential in n. Whenever n is not too large, you should be able to find a G module that appears here, which does not appear here, which will imply that this surjection is then not possible. That was their idea. They laid down a bunch of conjectures. Some of those conjectures have been shown to not able to prove exponential lower bounds, but nevertheless, there are other ways of overcoming the conjectures. But the conjecture itself probably stands, but just to show that there is one module which occurs here, which does not occur here, that is probably not correct. That will not show you exponential lower bounds. On the other hand, if I can show you that there is a module which occurs here, but with a certain multiplicity, but that multiplicity is larger than the multiplicity that occurs here, then also this surjection is not possible. because this is a surjection of G modules. If that is the case, then that something which appears with larger multiplicity here, then this will show that there is no such surjection possible. This was one of their other ideas. Yeah, so let me move on. I think I've spent too much time on this. But is the problem clear still? Is the question clear? And have I made at least that question clear to people?
Okay, maybe I should ask you later.
Okay.
What is the idea of the optimization? So,
yeah, sure. We'll talk about that. Sure. Yeah. So now we are looking at a one parameter subgroup which is pushing F into G. So let us renormalize it. And now this is the geometric picture. Then that G is sitting here and F is being slowly pushed into G. And G appears here. And it turns out, so if I look at this tangent, this is in some sense like the next term in the expression of lambda t dot F. And this is what we call the tangent of approach, because this is indeed the tangent of approach in this polynomial space by which F approaches G. Yeah. So we call FB the tangent of approach. And so we make one assumption that the vector space spanned by these other polynomials sort of intersect the tangent space to the orbit of G transversely. So this is an assumption that we make. So this is the geometric picture to keep in mind. F is somehow picking up G in its orbit closure, and this is the tangent of approach. Yeah. So then if I look at any point in this orbit, then if I look, that is now a point F of T0. If I pick up a particular point, suppose it is at time step T0, then now this is Ft0 times the determinant. And of course, its stabilizer is then just the conjugate of the stabilizer of the determinant. So I call K the stabilizer of F and H the stabilizer of G. So for me, K is the stabilizer of F. I have not where I write it. Sorry. K is the stabilizer of F. K is the stabilizer of F. So K is K of F. And H is G of G, the stabilizer of G. The stabilizer of G is H, the stabilizer of F is K. So please keep those two notation in mind. Yeah. So then if I give you the stabilizer of F, then at any other point, Ft0, then of course this is going to be the stabilizer of this point. It is just a conjugate because it's a point in the orbit of the determinant, of orbit of F. If I take a point in the orbit of F, its stabilizer is going to be a conjugate of the point I started off with. Yeah. So what we proposed what we've been looking at in the past few years is to look at not the stabilizers, but the Lie algebra of the stabilizers. So what is the Lie algebra of the stabilizer? So the stabilizer now for us is an algebraic group. It comes with its, so it's a subgroup of G. And as a subgroup of G, I can talk of its Lie algebra. Lie algebra is a subalgebra of the Lie algebra of matrices. So recall that the Lie algebra of GLW that we had is the set of all dimension W cross dimension W matrices. Now, the Lie algebra of the stabilizer of F, which is K, I denote by K. It is a Lie algebra under the standard bracket. If I give you two elements in the Lie algebra, their bracket is A times B minus B times A. Yeah, exactly the bracket that I have on on matrices. The Lie bracket on matrices is precisely the bracket I'm using. So what we try to understand is how this Lie algebra finally gets into, so now G has its own stabilizer, which was H. Its Lie algebra I will denote by subscript of H. And our approach has been to try and understand how this Lie algebra deforms into the Lie algebra of G. Yeah. So this is what we study. And this is really what I'm going to describe in the next, whatever, 20 minutes, 25 minutes. Is this clear? Are there questions on this? We want to understand how this Lie algebra.
Yeah, yes, clear. Thank you. Yes.
Okay. How this deforms into the Lie algebra inside this. Okay. So what we actually show is the following. This is what I'm going to talk about. So there is a one parameter subgroup which is pushing f into g, which is pushing f, capital F into little f into little g. What we are actually showing is that now at every point t, so this one parameter subgroup, I can talk about what is the base. So at point t, the stabilizer, if the stabilizer Lie algebra, if I call that k of t, we are trying to understand this in the limit as t goes to 0. So I denote, so what we actually show is that the limiting process yields a Lie subalgebra of script h. Yeah, this Lie subalgebra k hat we can describe precisely, and we show that this limiting Lie subalgebra actually goes into H. It has the same dimension as the Lie algebra of K. Yeah, and this establishes the link between the stabilizer of F and the stabilizer of G that we were looking for. This deformed Lie algebra at t equal to 0. We also point out the importance of the tangent of approach into G. Yeah. And then we do something more. We also describe something called alignment. And we describe how this limiting process, whereby K gets into H as a Lie subalgebra K hat, we describe how it allows us to possibly construct intermediate varieties between the two orbit closures. Note that the orbit closure of G is sitting inside the orbit closure of F. So ideally, we would like to understand modules which occur here, G modules which occur here, and G modules which occur here. We say hopefully that these intermediate varieties will allow us to give us a more nuanced understanding of these G modules which occur. Yeah, we would get a better lens to try and understand representations, maybe even try and understand the optimization route to this problem. So this is what I'll be talking about. So I'll need a few preliminaries. Let me come to that. But if there are questions, please halt me, because I will need to get into some elementary facts on Lie algebras and weight theory. So I will describe that, and then I will show examples of how these Lie algebras, sort of what the limiting Lie algebra is. Okay. Are there questions? No? Okay, then I'll go ahead.
Just 1 second. One quick questions. One quick question about your earlier definition of polynomial picked up by one parameter subgroup action.
Yes.
You mentioned if polynomial G is picked up by one parameter subgroup acting on F, then they cannot have distinct stabilizers, but that's not quite true.
So along the orbit, the stabilizers are just going to be conjugates of what I start off with.
Along the orbit, but then
but in the limit, I know what I'm picking up. I know its stabilizer. Its stabilizer I called H, and the stabilizer of the form I started off with I called K. What we are actually saying is there is a way that the Lie algebra of the stabilizer of K gets deformed into the Lie algebra of the stabilizer of H. This is what we are actually going to show, that this lands up, that stabilizer gets, the Lie algebra gets deformed, it gets twisted, and it eventually lands up into H. That is what we are showing. So that is the connection that we are establishing. So for example, if you can show that K hat is not a Lie subalgebra of script H, of cal H, then you're done.
Right, but in terms of this expansion of the action of one parameter subgroup, in terms of this terms,
Yes, it depends upon the one parameter subgroup.
So these points in the limit, you obtain them by looking at leading term, right? And
Yes, that's what we are going to do. We are going to look
okay,
at
and this polynomials in leading term.
yes, that's what we are going to do. Yes.
They are all limiting polynomials. Okay.
Yeah. So an example will make it clear. I'll come to an example soon. Yeah. Yeah. We'll come to an example soon. Okay. So I will need the following that there is G. G was acting on my G, of course, acts on itself by conjugation. Therefore, it acts on the Lie algebra, and this is the action of G on the Lie algebra via conjugation. You take a matrix and just conjugate it by G, and you get another matrix. So this is what is called the adjoint action. Now, there is also, note that we all started off with the representation of G on a big vector space, which was Siemens of W star. So there was this, and now this gives me actually, this action is a polynomial action and actually gives me a corresponding map between the Lie algebra of G and the Lie algebra of GLV. Note that the Lie algebra of G is what I called script G. The Lie algebra of GLV is all endomorphisms of V. And this is what happens, that there is a Lie algebra action. So if I now take this little g, it actually goes in here. And now I get a nice action of rho g on elements here. Yeah, so one can actually show that this is also true. That rho g of, if I look at an element here and I see what is its image, and now I conjugate it by an element of capital G, it will go precisely into this. It is precisely, you can conjugate it first and then send it via this. So these are two things one should remember. Yeah. Yeah. So whether I first conjugate it and then I push it forward by this map, or I push it forward and then conjugate it by the action given by rho, I will end up with the same element of NV. Yeah. So these actions are compatible. That is important. Okay, so I will need one more thing. If I give you a one parameter subgroup, a one parameter subgroup is really a map from C star to G. Yeah. Now, if I give you this one parameter subgroup, then of course this one parameter subgroup gives me a natural decomposition of V by weights. Yeah. What is the thing? If I look at how it acts on a vector, I can look at if it acts on the vector by a scalar, by scaling it up by t to the I collect all those vectors in what I call V sub I. Yeah. So every one parameter subgroup gives you a decomposition of V like this. Because of one parameter subgroup, you can, because it's a one parameter subgroup, it's a abelian subgroup. So I can actually find that they're all diagonalizable, they're simultaneously diagonalizable, and therefore I get this decomposition of V. Yeah. And I can therefore say V is direct sum of these VIs, where an element in VI gets scaled up under the matrix lambda t by t to the I. So that is the weight. I call this the weight of this vector. Now, of course, this one parameter subgroup is an element of G also. Since it's an element of G and G acts on G, yeah, I get a split of the Lie algebra of G also. I get a weight decomposition on Lie algebra of G also, and that I denote by this. So in GJ, I pick up all those elements of my Lie algebra where this one parameter subgroup acts as T to the J times G. Yeah. So I have this decomposition of the Lie algebra, and I have this decomposition of my vector space V. So I have these two decompositions. Now, furthermore, if I look at a vector and I look at its decomposition with respect to the one parameter subgroup, and I give you a Lie algebra element and I write down its decomposition with respect to the one parameter, so its weight decomposition, then of course, like we said, this little g, if I give you a little element g here, under rho, it is going to some endomorphism. Therefore, it acting on V via that endomorphism, I can say, well, what happens? What is the breakup? What is the weight space decomposition of GV? By GV, I mean row 1 of G acting on the vector V. V has this decomposition, G has this decomposition, then this will allow us to conclude that the image of G under the image of V under this little G, if I write that as W and I write down its weight decomposition, it's not difficult to see that this Wi is going to be really this expression. The terms of degree I that I will see are obtained by this. So these weights add up. The weight J adds up with the weight I minus J to give me a vector of weight I. Yeah. So grant me this. I'm not going to prove this, but just grant me this. So I have a decomposition of G in terms of the weights. I have a decomposition of V. And then I claim that this is the way GV is going to break up. It is going to break up like this. So this is going to be important for our results. So now I can talk of, given any vector V in my vector space, it has this weight decomposition. I can talk of the smallest weight that appears in the decomposition. I call that the degree of V. Likewise, for any element in the Lie algebra, I can talk of the smallest weight that appears. Yeah. So then what one can show is that if I look at the degree of the bracket, so this is a Lie algebra, if I look at G bracket G prime, the degree of this is the sum of the degrees of G and G prime. Yeah, if the degree of the bracket is the sum of the individual degrees, yeah, then if D is equal to D, then in fact, if this happens, then the leading term of this bracket is in fact, you can get it by taking the leading term of G, taking the leading term of G hat, and taking their own brackets. Yeah? Note that G hat and G prime are also in my Cal G, therefore their bracket makes sense. Yeah. Yeah. But on the other hand, if this happens, if the degree of the bracket is more than the degree of G and G prime summed up, then one can show that the bracket itself is 0. The bracket of the leading terms is actually 0. And this is a straightforward calculation. Because if I look at this expression, if I'm calculating this, the degree of this I obtain actually is G comma G prime. The bracket of this is really the bracket of G of t with G prime of t. But I know how to write G of t in terms of its decomposition. It is Ga times t to the a. There is t to the a, and this is the term of degree a in my G. Then there are higher order terms. This is the smallest degree term. So therefore, the smallest degree term that will actually survive is t to the a plus b, because these two multiply out to give me a term of degree a plus b, and this is going to be the smallest degree term that I will get. And I can write down this, yeah, and there is going to be no other contribution to this. It is only going to come from GA bracket GB prime, because all the other terms here have higher degree than B. So their brackets are only going to give me things which are higher than A plus B. So I will be left with this bracket as the coefficient of A plus B, as the coefficient of t raised to A plus B. But that is precisely this is what I have defined as G hat. This is what I have defined as G prime hat. So this bracket is really this bracket. So now, of course, if this bracket is 0, then the degree of this is going to be something larger than this, than A plus B. Yeah. So I will need to define what the degree of 0 is. I'll define the degree of the 0 element to be infinity. For this, of course, that is the only other case that I need to worry about. So what we are saying is, I have to just look at the bracket of two terms. Either it's going to be if I look at the least degree term that I will get, it's either going to be the bracket of the individual least of the leading terms, or it is going to be 0. So that is important. Yeah. Likewise, if I look at this expression, if I look at G and apply it to V, then either G has its own smallest degree term, V has its own smallest degree term. So let me compute G hat, V hat. Either G hat, V hat is 0, or if it is not 0, then G hat, V hat must be precisely G hat applied to V hat. Again, by the same sort of calculation. Yeah. The same calculation tells me that if this is non-zero, then the degree of this must be the degree of this plus the degree of this. Yeah. The same calculation tells you this. So therefore, if I look now at this, what we are actually saying is, if suppose I give you an element G and I give you a vector V, and suppose I already tell you that G dot V is 0, then this tells me that G hat applied to V hat must be actually 0. Yeah. So if I look at the stabilizer of V hat, it must contain all these G hats, which kill it. Every G which kills the vector V, if I look at their leading terms, all those leading terms must stabilize V hat. So this notation, sorry, I did not introduce. It is, you look at V, look at the stabilizer of V and take the Lie algebra of that. So what we are saying is the Lie algebra of the stabilizer of V hat will always contain the leading terms of the Lie algebra of V. Take all elements which stabilize V in the Lie algebra. For each of those elements, you take their leading terms. All those leading terms will have to come in here. Yeah. So that gives you this proposition that if I start off with F and I pick out G in the closure, yeah, then so recall K was the stabilizer of F, H was the stabilizer of G. Then this calculation tells us that K hat, the leading terms of all the algebra elements in K, will have to end up as terms which stabilize the Lie algebra of terms which stabilize G. Yeah, because so this is if G is the leading term, because G is really the leading term of F, then this statement that we just proved proves this. The leading term of G was of F was G. So we are saying the Lie algebra of the stabilizer of G contains the leading terms of all of the Lie algebra of the stabilizer of F. So here is my F and here is my G. GF hat is contained inside G of G. That is precisely this statement. Because this is GF hat and this is G of G. Is this clear? So this is how these elements get into this. All the leading terms. So you write down K, write down all the leading terms of every element in K, all those elements have to get into H. So let's do a simple example. Yeah, and one can show that the dimension of this is the dimension of K. Yeah. So this object, this K hat, and this calculation tells us that it is actually a Lie subalgebra. Because two elements either their bracket is 0 or their bracket, if the bracket is non-zero, then that will survive inside K hat. Yeah. So that I'm not going to show now, but let us look at an example. Let us look at two examples. Yeah. So is the statement clear? Does anyone have a question on the statement? So this is really the statement. GF hat is contained inside G of G. Yeah. Is there a question on is the statement clear? Are there questions on this? No? Okay, then should I go ahead?
Yes, please.
Yeah. So now take this form. Let us start off with this form. X1 squared plus X2 squared plus X3 squared whole square. Yeah. So it is not difficult to show that. So this is a really quadratic form. And this quadratic form square. So this quadratic form is stabilized by these bunch of matrices. These are really, and the Lie algebra is the Lie algebra of the orthogonal group actually. So it is, so if one can check this. So for example, if let us just assume that this is the case, that this happens. Now take this one parameter subgroup. How is it acting? It is keeping x1 as it is. It is keeping x2 as it is. It is scaling x3 by t. So this polynomial is going to go to x1 squared plus x2 squared plus t squared x3 squared whole square. That is how this one parameter subgroup is acting on this polynomial. Yeah. So what is the limiting polynomial? The limiting polynomial is x1 squared plus x2 squared whole square, because this is fixed, this is going by t squared. So in the limit, as t goes to 0, this term will vanish and I'll be left with these two terms square. That's what G is. Yeah. Okay, so what is the stabilizer of x1 squared plus x2 squared? What is the stabilizer? So now I will, so really this x1 is going to go to, so this is the Lie algebra of the stabilizer. So really it is going to be sine theta, cos theta, sine theta minus sine theta, cos theta. And really I don't care about what x3 is. So that is what is captured here. If I look at x1 squared plus x2 squared, of course, if I multiply x1 by cos theta plus cos theta x1 plus sine theta x2, and then I square it, and x2 I multiply by minus cos theta x1 plus sine theta x2 whole squared. That's going to give me back this. So that's how I get this part. And x3 I really don't worry about, yeah, because x3 is free. I can send it to whatever I want. So that is what the Lie algebra of G is. Yeah. So now let us look at, so what we said was I have to take the Lie algebra, the action of lambda t on the Lie algebra of G of f. So when I multiply this out by conjugation, I get this. So let us stare at what will survive in the limit. The smallest degree terms, as we see, are -1. So if B is not 0, I will certainly get a matrix where, I suppose B is not 0 and C is 0. I will get, in the limit, I will certainly pick up 0, 0, T inverse B. Yeah, that's what I'll pick out. I'll pick out this element, which is a free element that I have. On the other hand, maybe B is 0 and C is not 0, in which case I'll pick up the matrix 0, 0, 0, 0, 0, 1 and 0, 0, 0. Yeah, so that's corresponding to this C, 0, 0, C. So that's what I will pick up in the limit. Yeah, the coefficient of T is what I need to write down. The coefficient of the smallest degree term here is C, so that's what I'll pick up. On the other hand, both B and C may be 0, in which case the smallest degree term in T that I see is T raised to 0, because this has T raised to 1, this has T raised to 1. The smallest degree term is this. So then I will get this. So GF hat is spanned by matrices of this kind. Matrices where A, B, and C are allowed to vary, but matrices of this form. Yeah? And of course, if you observe this sits inside this. GF hat sits inside G of G. The Lie algebra, the leading term Lie algebra sits inside the leading term inside the Lie algebra of the stabilizer of F. So maybe I don't have much time. Maybe I will just look at one more example. Yeah, to tell you that it is important to understand how.
So
lambda-
yeah,
Sorry.
the amount of time, I think about roughly 5 minutes, something
More?
like this.
Yeah. Okay. So, but I hope at least. So this is the important, the most important point, that somehow we are saying that the Lie algebra gets deformed, and this is the way it gets deformed by a one parameter subgroup. And this calculation also tells you how you are going to compute k hat. You start with the most negative exponent in t, the smallest exponent in t, pick up Lie algebra terms that I will get from that, then pick up the next terms in t and so on. That is the way you're going to construct this filtration. And you can explicitly, if you give me k, give me a basis of k, and you give me this lambda, I can tell you precisely what is the basis of k hat. And we're saying this k hat has to go into H. Yes, that is the one of the main theorems. There are other theorems which I had this thing, but anyway, I don't think I'll have much time to explain that. But what also matters, which is what led us to define these other things called alignment and so on, is how the x and lambda t, I have a point f. How does the Lie algebra of k look? What is the pose that the Lie algebra of k presents to lambda t? That is very important, because k is there, lambda is there. I am taking lambda t, k, lambda t inverse. How k is presented, namely what we call the pose of k, is important. For example, here is a simple example where GL4 acts on 4 cross 4 matrices by conjugation. Let me take this particular lambda. Then, of course, when it acts on 4 cross 4 matrices, I can think of them as independent 2 cross 2 matrices. This is fixing all of it. So I get this. So this can be shown to be the action. M11 is the first 2 cross 2 matrix. This is M12. This is M21, and this is M22. This is the way it's going to act. And so now it's very clear that when I look at the sorry, I made a mistake here. Lambda t, m lambda t inverse. Okay. So now it is acting by conjugation. Yeah. So if I look at, of course, when it is acting by conjugation, and what is so if I pick up, so I didn't write down. So I'm sorry. What was it here? Sorry. So T inverse, yeah. So yeah. So let me assume that I start off with a matrix which has zeros here, and something non-trivial here and here. Yeah. Yeah. So maybe the same matrix here. So let me take this zeros here. Then when this acts on those kinds of matrices, of course, the leading term then, so this has vanished. The leading term only picks out this matrix and this matrix. So let me pick out let me pick out matrices of this kind. Matrices of this kind, x and x, and 0, 0. So the way lambda t acts on this is really, it is going to pick out x and x as its in the so k is going to be, no, sorry, I'm sorry. I pick out this family. I pick out this family, and now I apply lambda t to it. When I apply lambda t to it, I will see this term. I will see 0 here. I will see 0 here. I will see this term. So this term and this term survive, but they are the least degree terms. So k hat is actually k in this case. Yeah, if I'm applying lambda t to this Lie algebra, then k hat is going to be k. But this same Lie algebra, if I had, note that we are looking at conjugation, I could have given you a different pose of this Lie algebra. The Lie algebra remains the same. Up to conjugation, it is the same. But if I start off with this matrix and I apply it to my k, if I conjugate it by this, then this is what my k hat looks like, my k prime looks like now. Now, if I apply my lambda t, this is what I'm going to get. Yeah? And a similar calculation to what I did. So look at the -1 degree terms. That this is the -1, this is -1, this is -1. So I get, if this is non-zero, I will get an element corresponding to that. Otherwise, if this is 0, then I will get the same element C corresponding to this. But if all three are zeros, which means C is 0 and D minus A can be is also 0. So A is equal to D. And then I get C equal to 0. So I get 0, 0, B. So the K hat in this case is going to be matrices of this kind. So note that in the orbit, it is the same because I'm looking at the conjugation action. So these two elements are in the same orbit under conjugation. But if I start with this pose, what I end up with as K hat is actually a reductive group. It is really a copy of GL4. But if I do this, I end up with something which is not reductive, it is solvable. So that is very important. And this is what leads us to define these other notions, which we call alignment and so on. Yeah. So, but I unfortunately, I don't.
Yeah, thank you for your examples. Yeah, unfortunately, there is no time, I think, for, for the rest.
But I hope at least the main idea is really how K deforms into H. And that is really the connection that we first want to establish. And then this is what we want to exploit to define intermediate varieties and also to define this notion of alignment. Yeah. Yeah.
So now,
are there any other questions?
Yeah, now maybe it's right time to ask for questions from the audience.
Yeah, sure.
Well, the talk in general.
Yes, I would like to have, of course, there are many things. First, I was very intrigued how you can apply, what is the idea of optimization that you find some function.
Yes, so I will come to that slide. So that was somewhere here. Yeah, so this is one of the many attempts actually. So if I give you, like I said, okay, let me come to this slide. Yeah. So what we want to know is, does G belong to the orbit closure of F? That is really what we're interested in. That there is my G, there is my F. Can G belong to the orbit closure of F? This is a question of interest. Okay. So now suppose I look at, so we know this, we know good algorithms in certain cases. That's what I wanted to say. So for example, if I give you a bunch of matrices, yeah, suppose I look at all, these are all n cross n matrices. Or I give you even a single matrix and I look at GLN acting on the left and on the right by conjugation. And I want to know when will it pick up some other element in its orbit closure. Yeah? Or I give you a bunch of matrices and I look at, I can ask the same question. I have a matrix. I look at SLN acting on it by conjugation. And I give you another matrix. Will a conjugate of SLN pick up this matrix in its orbit closure? So SLN is acting on this matrix by conjugation. I give you a family of matrices, yeah, and I can ask you, here is a bunch of matrices. SLN cross SLN is acting on the left and on the right. It is sending a tuple of matrices to another tuple of matrices. Yeah. Then I can ask, is there a way of maybe I should write this a bit, okay, I'll write this here. So I have a bunch of matrices, yeah, and I have SLN cross SLN acting on this, on the left and on the right. Maybe every element transforms this bunch of matrices to another bunch of matrices. I have x1, x2, x3. I want to know if these matrices can be pushed to all zero matrices via SLN cross SLN action. I give you a bunch of matrices. I give you this tuple. and I asked you, can you push this under GLN cross GLN? So sorry, I'll have to say GLN cross GLN action. Yeah, I want to know whether you can push this to 0. So I can set this up as an optimization problem, and I can show, if you give me, so there is an algorithm which, given a bunch of matrices, will tell me whether they can be pushed towards the all 0 matrices. So that is what these kinds of optimization algorithms. These, for certain group actions, we know this actually. So this is, so when I push a vector in a vector space to 0, yeah, this is what Hilbert defined as the null cone of the action. So you have G acting on a vector space, the set of all V such that G dot V can be pushed towards 0 in the limit, is what Hilbert called the null cone.
Yes.
Yeah. So null cone membership for the left-right action. Yeah, null cone membership for the conjugate action. For those kinds of things, we have polynomial time algorithms. Yeah. So it is conceivable, if I give you F and G and I ask you if G is pushed, if G is captured by F in the limit, maybe there is an optimization algorithm you can set up which will allow you to conclude that no, F cannot be in the limit of G, that G cannot be in the limit of F. Maybe. Because if you do that, and if you give, so for example, if I start off with the problem that we were interested in, which is the permanent versus the determinant, yeah, and if magically, if you are able to show me that this polynomial, that this polynomial can never be in the orbit closure, you can give me a polynomial time algorithm which will detect this. Then you have done the job.
So what is the optimization of some how to say action?
So these are, yes. So these are, so what you actually do is you are trying to push it to 0, and you set up a appropriate objective function. Yeah, what is called the capacity of a bunch of matrices. So that is one way to do it. Yeah. So you want to understand. Because if so the optimization problem here is really this. Okay, so here is the vector, here is 0. Now, is the orbit of this, can I give you a bound on the distance of the orbit closure from the 0 point? I want to minimize the distance of the orbit closure to this point, to the 0 point. That is the optimization problem that you set up. Minimize the distance to the orbit closure.
Okay. But
yeah, but you can actually set this up nicely and you can solve this in some cases, not in all cases. We don't know it. So these are good problems that we would like to understand.
Okay, thank you.
Yeah. So what you're trying to minimize is the distance to the orbit closure from the origin. You can show that either it comes arbitrarily close, in which case it's going to go into the null cone, or you can show it is bounded away. That is the way you set up the problem. Yeah, okay.
Yes, so
Any
thank you.
question? Yeah, sure. Any other question? Yeah, sorry, I couldn't complete, but I at least hope I got across the idea that how this Lie algebra gets deformed into the other Lie algebra. That is really what I wanted to convey for sure. Yeah. Yeah. Okay, no more questions?
Yeah, maybe I have one question. Yeah, it's rarely the case that we can that we can compute this k hat. I mean this limiting Lie group. Right? For example, for determinant, we don't know much about.
For determinant, look, okay, so there are other theorems that we have. So, okay, so if you give me a k, you give me a lambda, I can actually compute k hat. That is not difficult. Okay.
Mhm.
So what we want to understand are, so I know that k hat, for example, has the same dimension as what I started off with. So one of the problems which you could potentially solve this way is to understand codimension 1 orbits. Because then in the limiting Lie algebra has to pick out one more element really to complete it to a Lie algebra.
Mhm.
Because the codimension 1 orbits have stabilizers which are of dimension 1 more than what you start off with. So one of the things we believe in is that perhaps this may give you some approach towards understanding the codimension 1 orbits inside the determinant orbit closure. Codimension 1 orbits which are picked up as limits of 1 parameter subgroups.
Mhm.
There are codimension 1 orbits which are not orbit closures of forms, but I mean, we believe that one should be able to get hold of these codimension 1 orbits. I mean, that it is conceivable that you may get information about the codimension 1 orbits. Yeah, and if you get codimension 1 orbits, then perhaps you can move on and slowly induct downwards. Perhaps, of course, these are all wishful thinking, perhaps, but yeah. But there are some other theorems which we have here, which tell us how the limiting algebra. Yeah, so maybe I should just sort of flash that theorem, because that theorem is actually, I think, an important theorem for us. Yeah, yeah. So if I look at this, so you have k hat, and so let us. I mean, I don't want to define that. I don't want to keep you for too long here. Yeah. So if I look at this object, L bar is another element. This is really the tangent, the tangent of approach. Yeah. If I normalize the lambda so that G is picked up as a degree 0 term in T. Yeah. Then that is a 1 parameter subgroup. Therefore, correspondingly, there is actually a Lie algebra element corresponding to the 1 parameter subgroup. That is what L bar is. So now we have this very intriguing theorem which tells us that if I look at k hat and I just append to it that L bar, then either this happens, that k prime, this is, one can show that this is also a Lie algebra in its own right. Yeah. Either it is a Lie algebra of rank 1, which means that it has, this is the only rank 1 element that I don't really see by, so rank 1 means that the dimension of the maximal torus here, the maximal diagonalizable maximal torus that I see here is actually 1. Or if that does not happen, then in fact, that variables in G and variables in F are nicely linked. Yeah. So this is what we call alignment actually. Yeah. So for, I mean, the motivation for that, let me just take another minute of yours. So what we are saying is either this happens, and we believe this will not happen when the limiting form that you are picking out is a form with a distinctive stabilizer. What will happen is this. This cannot. So either this has to happen or this has to. A has to happen or B has to happen. And we conjecture that A will not happen when G has a very distinctive stabilizer. Which means something nice should happen. And what is that something nice? That both K and H actually share some semi-simple element, some diagonalizable element. And that gives you some relation between the variables that occur there. I'll just show you briefly by a picture and I will stop. So look at Grenet's construction of the permanent. This is how Grenet constructs the permanent for you. So what happens in this case is if I look at if the left matrix denotes the permanent variables and the right permanent variables and x77, which I have added for a padding purpose. Yeah. So what Grenet's construction tells you that if I look at the variables that are occurring in the permanent, namely x11 up to x33, they go into nice rectangles inside the determinant actually. determinant variables. This, for example, this yellow patch here can only go as two rectangles. This blue patch here goes as another rectangle and another rectangle. There is a partition of the variable set of the determinant and a partition of the variable set of the permanent, so that rectangles go into unions of rectangles. Somehow those subspaces of the corresponding hypersurfaces have some kind of alignment, is what we are saying. And that happens, for example, in Grenet's construction. If I look at x11, x12, x13, they will appear only here. They only seem to appear here, inside this rectangle. A rectangle. So I have written this down, so maybe you can look at it leisurely. So here is the variables of here is the partition that I have for the variables. I can draw rectangles for the permanent. I can draw corresponding rectangles for the determinant. And Grenet's construction also seems to suggest that something like this is happening. Curiously, we believe that even Landsberg-Rasaille's exponential lower bound for the equivariant complexity, determinantal complexity, also has this kind of a behavior. There is some partition of the variable set which sends one to the other into unions of rectangles. Rectangles here can only go into unions of rectangles. There is something like this seems to be happening, and which I think is completely worth exploring. Yeah.
All right.
So
Thank you very much.
Okay. Thank you. Yeah. Okay. Thanks, Fedor. Yeah. Bye.
Yes, so let the thanks the speaker, yes.
Okay. Thank you.